well, I'm planning to show you 2 exercises. Probably we will only be able to do the first one completely. The second one, I hope that we have time to just begin it, and then we can continue it during the next lecture. So these 2 exercises require you to download some code that I've prepared, some scripts and some C code that I've prepared, and then modify them a bit. We will come to that in a few minutes, but if you want to already, you can try and check out. So basically the GitHub repository that I ask you to use to check your installation, to check if you have all the prerequisites for this hands-on practical. If you go back to your local directory and if you fetch the new branches using git fetch, and then you check out the branch exercises, then you should be good to go for the 2 exercises above. So you should. So we'll do this again if you don't manage to do it now. Okay, so I'll just repeat a few slides that I had during the first lecture to just refresh what we said a bit about the data layout optimizations, which I will which I want to demonstrate to you today through these exercises. Okay, so we had said in the first lecture that most modern processors that you find in HPC systems, and actually in any computer, but most notably in HPC systems, in supercomputers, have some vectorization capabilities. And what that means is that they have some special functionality that allows them, so special hardware that allows them to do to do the same operation on multiple data in parallel. Okay. To give you an example, and I showed this example also in the first lecture. If you have so this is a very simple operation, but it's just to show the point. So if you have an operation like this, where you have a vector x and an array x and an array y, you want to multiply each element of x by a scalar, add it to y, and then put it back element by element into y. Then you can see that for every index I of this array, you're basically doing the same operation. So if I write this 4 iterations at a time, and it doesn't have to be 4, but just for the sake of demonstrating it here, if I just unroll this loop, we say, well, I unroll this loop for 4 iterations at a time, you can see that basically you're doing a multiplication by a scalar and an addition in every iteration. And okay, and the point I wanted to make was that there is special hardware on well, almost any CPU architecture that is available now, where basically this does not require well, I don't know, I mean, how many operations are we doing here? Basically we're doing 1, 2, 3, 4, 5, 6, 7, 8 floating point operations, right? 4 multiplications and 4 additions. So the special hardware that I'm talking about allows all of this to happen in basically maybe even 1 clock. So in basically one big operation, let's say, that requires 1 clock update and throughput. And so you can imagine that what you really have on the computer is a vector, a kind of vector float type instead of just a simple float type. And then there is a way to load 4 elements at a time of each of the vectors, as I show here. And then this operation done like that will happen in one clock. Okay. So in many cases like this one, where it's very trivial, the compiler can do this. So you don't need to do anything special. You just write your code like this, and the compiler will see it and will say, this is an opportunity to vectorize, so it vectorizes. So if the data is laid out in a specific way, or if it's a very simple operation like this one, then the compiler will do it for you. There's nothing that you need to do. This is, so I gave you this trivial example where this is the case, but this might not generally be true. So you might have code where this is not generally true, and then you as a programmer have to think about what to do in order to facilitate this kind of vectorization, okay? So, so what we will look at today and in the next lesson as part of the exercises is to make transformations to our data layouts so that we assist this auto-vectorization. By the way, this seems like it's a transformation that will optimize the floating point operations that we're doing, but really what we're also optimizing is accessing the data in a continuous way, so that we're also optimizing how fast we can read the data from memory. So this is so we actually win when you have this data layout, even if your code is memory bound, let's say, then these kind of optimizations can speed up how fast you're actually accessing the data, and not just how fast you're doing the computations. Okay, so it would be trivial if we just did this as an exercise, because as I said, even for even if you don't do anything, you're probably already taking advantage of the vectorization. So I've set up an exercise for you, which is still a bit of a fake exercise, but that will demonstrate a bit better how with a very small transformation you can see big speed ups in the runtime of your code. So what I've set up is an exercise to demonstrate how you go from well, an array of structures to a structure of arrays. And I'll explain a bit what this means. So imagine, let's say, this is just an example that you have a set of coordinates that you want to represent in your code. Okay, so if you're familiar with C, then what you could do is have a structure like this. So you have you're basically defining a new type, right? Like you have a double type or a float type, but this type has 3 members, X, Y, and Z. Okay, and then you can allocate 1,000, let's say, elements of this structure like this, so that every element now of the array has an X component, a Y component, and a Z component. Okay, now if you want to do some operation over the coordinates, in this case, what I'm doing is I want for every element of this array, I want to get X squared plus Y squared plus Z squared. So I want to get, so there's a typo here, there shouldn't be a parenthesis there. But anyway, so I want to sum the square of the coordinates, okay? Then you can see that this operation is not very easy to vectorize. And I'll show you a picture later that shows you why this is not very easy to vectorize. So typically what we do is we make a small transformation in the data layout in order for such operations to be more, to be easier to vectorize. So, a way to see this is you would make the structure not be a structure of just scalars, but a structure of arrays, right? So from array of structures says the title to structure of arrays. So then each element is its an L length array. So we're sort of transposing the order of what goes fastest. Does the component of the vector run fastest, X, Y, Z, or does the element of the array run faster? So we're swapping this around. And then if you unroll this out like it did before with that simpler operation, you can see how this is more easier to vectorize, because now for each element of the array, you have nicely lined up the operations, and now you can do this in, you know, in less number of these vectorized operations. So just to give you a picture of what this looks like. So in the original layout, right, you had an array which each element had X, Y, Z. And so basically how this was laid out in the memory was that, so the first element would be this lighter blue here. So that would be element 0, component X, element 0, component Y, element 0, component Z, and then the darker blue here is then the next element, so element 1, component X, element 1, component Y, so on. And so that when we would try to read this, right, continuously and put it into one of these, let's say, float 4 vectors, which I showed before, then this is how this would be put in, right? And then this is how they would be put into the next one of these 4 component vectors. And so now, remember, the operation we want to do is X component of 0 times itself, plus Y component of 0 times itself, plus Z component of 0 times itself, and then sum them. And you can see that in order to do this in a vectorized fashion, then what I need now is temporary variables of this type in order to reshuffle the data so that they line up. And that's what causes this inefficiency that you want to avoid by doing this transformation. So if I have the new data layout now, which I put down there below, basically what I'm doing is I'm, you know, as I said, I'm transposing what runs fastest. So now the I index of the array runs fastest, and I have I have X component of the 0th element, then X component of the first element, then X component of the second element, so on, and then start the Y components. And so now if I load this into vector registers like this, you see that this is lined up nicely so that I can do this times itself will give me X squared of the 0 element, X squared of the first element, etc. And then this times itself will give me the square of its of the Y's, and then I can add them together in a vectorized fashion. Okay, so this is what I've set up for you to do in the first exercise, and I'll say a bit more specifically what you need to do. So this first exercise is, so if you go to, as I said, the repository you used that I gave you in order to check your installation, and you do a git fetch, then this will fetch the new branches. You git check out exercises, and then you will see a new folder or directory which is named like this, AOS-2-SOA. And if you see the Intuit, you see these files here. So what is implemented in here, and I'll go through the code a bit with you, is sort of what I talked about last time in the previous slide, but a bit more involved. So basically, what you have in this code is initialization of an array of 4 vectors. So you can think of it as, you know, a 4 vector, like a space-time vector, which has a t component X, Y, and Z. And what we want to do is, for every element, we want to compute this, you know, this Minkowski norm. And then this code, what it does is, so it allocates a long structure of these 4 component vectors. Then what it does, it computes this S for each element, and then it reports the time. Okay. Now, if we were just going to do this, if we just did this once, then the time would be very noisy, right? We need to do this repeatedly in order to get an accurate measurement of the time. So we have to go through, so in order to have a reliable timing, the code does it multiple times. So you don't have to understand all of this part of the code completely, but basically the main operation that is being done is this comp S here. That's the part that actually does the calculation. And this is done some number of repetitions, and then in turn this is done multiple times, and it does this until the variance of these times is narrow enough that it can say that this is timing. So if you want, you can take a closer look at this. You don't really need to in order to finish the exercise. It's just a mechanism to get an accurate value of the timing. The timing itself is done here. So there's this function which is defined a bit higher up in the code, which is called stopwatch. And so you take the timing here and the timing there divided by the number of repetitions. And now T0 has the time between these two lines in the code, sorry, divided by the number of repetitions, okay? Yeah, so that's what it says there. So in the end, when this loop finishes, this variable here, T0 ACC for accumulated, T0 accumulated, is the average time per call of this comp-s, okay? And that's just the definition of the stopwatch function. So it just returns the time interval between now, the time you call it, and the first argument that you put there. Okay, so we begin by having a structure like the one I showed before, but now there's more components to that. It's XYZ and there's also the S that we need to calculate, and this is where the calculation is done. Okay, so again, this code is calling this comp S multiple times, and this is the definition of this comp S. So what it's doing is basically T times T minus X times X plus Y times Y plus Z times Z, and then it's putting in an S. There's also some parallelization up there. But the parts that you need to fix is down here, okay? So somewhere in the code, and again, I'll show you the code. If this all looks a bit daunting right now, I'll open an editor and show you the code. What we want to do is, at the end, we want to report the floating point rate in gigaflops per second and the bytes of I/O in gigabytes per second based on the timing. So we know how much time it took, average time it took for this kernel to run, however number of times it ran. And we want to basically do what we also talked about in our previous lectures, both in the last one and the first one, where you want to count the number of floating point operations that are required per element of the array, and from that divide by the time and get this sustained gigaflops per second. And similarly, we want to count the I/O operations, so how many bytes are read and written from memory, and fill this in, this beta I/O, to report the sustained bandwidth. So once you complete this, then there's a make file, so that if you type make A, it will compile the code. So this you will just see echoed to your command line. And then you can run a prepared shell script, sh-run-a.sh, which will basically run this for varying the length of the array. Okay, and then once you're done, then this should produce the text file with the results, and then you can plot the results, which will be the performance as a function of the array length by running this Python script plot_a.py, and this will produce, I think, a PNG or a PDF. I think it's a PNG. Okay, so that's what I would like you to do, and I'll give you some time to do it as soon as I just go a bit through the code. with you. So I can bring it up here. Just a second. Yeah, okay, so let's just a second so that I can. Okay, maybe I start like this. So maybe I'll make it a bit big. If you can't see it, tell me and I can make it bigger. Can't see the text. Okay, but this is something that you should have already done, but I'm just cloning it again. Okay, if I clone it like this and CD into it, then I'm in the prep branch that you already should have tried. I said git fetch, but this won't do anything because it's already fetched. And then check out exercises. And now, right, so there's two directories, EOS to SOA and lab. And what we want to CD into is this first one. Okay. And the first file that we will work on, as I said, is space-time AOS. Okay, so I'll bring a text editor into the shared screen. Just a second, so that I can open it. So we said space-time AOS. Okay, right. It's a bit too small. Let me try and make that. Oops, just a second. Okay, that should be large enough. Can you see that? If you cannot, please say so. Okay, I'll give you some time to look at it. Just let me get the important points. So here's the structure. It has X, Y, Z, T, and S components. That's just the function stopwatch that we already covered. A facility to allocate memory, which again, you don't need to worry too much about. This just prints how you use the code. Okay. And this is the main kernel, which computes this S, okay? So it's pretty simple. It just goes over the number of elements, which is L. It grabs the X component, the Y component, Z component, and T component, and then does this min-cost norm and stores the result in array.s. And what you, okay, so here is the main program where it begins. It will grab the length from the command line, okay? And then it'll just fill X, Y, Z, and T with random numbers. Okay. And then this is the main loop that I also showed you in the slide, where it basically does this multiple times and takes an average. And it'll stop once the average time has an error which is smaller than 10%. Okay. And this is the pieces that I want you to fill in, basically. So it's basically just two numbers. You need to calculate, well, you need two expressions. One expression here and one expression here, beta FP and beta IO. And when you do those, when you run those two expressions, when you fill those two expressions and you run the code, then those will be printed here. Okay, just to show you what I mean. So I just put 0 and 0, although you need to calculate them somehow. So if I put 0 and 0 there, okay, so assume that I've got this correctly. If I plot it, make A, so that will compile it. Now I have an executable space-time AOS. Now, the way to run this is to space-time AOS and write, I don't know, 128 elements. Then that will plot I used 8 threads, L is 128, and it took so many seconds, okay? Average and error. And that is 0 gigaflops because I set it to 0. So for you, it should say something more meaningful and 0 gigabytes. But you're not exactly supposed to run it like this. What you are supposed to do is use this run a.sh script, which is also there. And when you run this, it'll basically do this in a loop for varying lengths. And so what we want to see is basically what the performance of this code is as we make the arrays larger and larger. Okay, so you will do something like sh run a. So I'll just get zeros all the time. But this is basically what will happen when you run it. If you have it correctly, you will not get zeros. Okay, it'll take some time. I mean, I'm running this on my laptop, which is, okay, not ideal. But that's what we have at the moment. Okay, good. This will have created a text file, aos.txt, which is exactly the same as you saw on the screen. Then this Python script, plot A, will generate, that's just a warning, a.png, which for me is just 0. But you should get something more interesting. Okay, so why don't we do that? Why don't we do that until 45 past? But of course, you can still just ask questions in the meantime. But everybody else, please go ahead and try and figure out what this beta IO and beta FP is. Fill it in, run it, and if you you can text me privately if you would like me to check whether what you put here is correct. You can text me privately about it if you just want to check whether that's correct or not. And I'm, of course, available for questions while you do this. Lorenzo, is what I said even possible for them to chat me privately?
Yes, I
that
think.
Doesn't. Yeah. Okay.
I mean, if not, let me know.
Yeah, there's a when you open the chat box, there is a box that says everyone. If you click on that, you can choose someone to message
Yes.
privately.
Daniel, sorry, you probably have the sound on yet still.
Oh, right. Thanks.
Could I please ask you just to text me to, I mean, there's two of me. One is the camera and the other is the sharing the screen. Can you please text me in the non-camera? I mean, in the box that is not showing my camera. I don't know if that makes a difference, but it seems to do make a difference. Yeah, okay, Giuseppe, thanks. Five more minutes and then I do it on my side. So yes, you can neglect operations in stopwatch. We're just counting the operations in Compes. Okay. I think it's time to do this. I got some correct answers. So let's see. So beta FP. So what we want to compute is the number of floating point operations per second. So we know how many times the we know how much time it took to call comp S, as I said. So the average time is in this T0 ACK, right? It says it here also. And okay, so this is actually already divided by the number of repetitions. So actually T0 ACK, this variable T0 ACK is actually the average time for one call of comp S. And so all we need to do is know how many, all we need to do is count how many floating point operations are done in comp S and how many bytes of I/O are written in comp S, and then divide that by T0 ACK. So if I scroll up, okay, so how many floating point operations are carried out in comp S? Well, there's floating point operations, right? Not integer operations, floating point operations. So there's a star, there's a minus, there's a star. These all are floating point operations. So there's 1, 2, 3, 4, 5, 6, 7. Okay, and this is done L times. So I have L times 7 floating point operations. So 7 times L floating point operations over T0 ACK. The bracket is not necessarily needed. Okay, and this is a large number. I want it in gigaflops, so I can also do something like this. Good. Now let's go to beta IO. How many bytes of data are read and written? So, well, in each of these iterations, for each iterator I, I need to read these 4 components and write 1. So basically I'm reading 4 floats and writing 1 float. So the total IO is 5 floats, so 5 times L, and they are floats, not doubles. So some of you put in double, so it's going to be 5 times size of float times L over T0 ACK. And okay, this could be 1024 to the 3, or just 10 to the 9. It doesn't really matter that much. Depends on I got a question. Does it accumulate the time of n runs? Yes, but it's divided by n here.
But this is this average, and down there you divide by T0 accumulated. And this average is also not visible outside this loop anymore. Ah, sorry. Okay, I got you.
Is it clear? Okay.
Yep, sorry.
Yeah, I think it's okay. Yeah, it should be T0 ACK, and that is the time for 1 call of compass. Okay, I think I'm good to compile it. Yeah, make a okay. Then I can run it. Okay, and as with any good cook show, I've already prepared the plots here. So this is sort of what you, well, I mean, you're on different computers, so I don't, it's not exact. It's not clear whether you should get the same or something similar. In any case, I run this on 2 computers. On the right, there's a node of a cluster which has 8 cores on 1 CPU. On the left, it's just my laptop. okay, my laptop does other things. It's not just running this benchmark, right? But you see a similar shape where you get a peak at small values of the length, and then this flattens out at about, in this case, at about 10 gigabytes per second. Here it's a bit about 15 gigabytes per second. So I think you should get a shape similar to this. So a bump and then flattening out somewhere. Okay, and how can we explain this? Well, I need to show you this picture again, where you have the CPU, the CPUs, the cores of the CPU, you have some cache, and then you have some memory. And what's likely going on here is that when you have small lengths, right, then basically the first time you run it, then all the array is read into cache, and then it fits in cache. So those repeated iterations we're doing of measuring the time, you're just basically reading from cache, okay? And so what you're seeing somewhere here in the middle is basically the time it takes. Either depending on what the bandwidth to cache is, it could be bound by the bandwidth from the cache, or it could be bound by the floating point operations, peak floating point operations. But in any case, what you're not measuring is the IO from memory anymore, right? But then when you enlarge the arrays as they get larger and larger, then in every iteration, right, you're filling up the cache and then some. And so that means that for every iteration, you need to reread the array from memory. And so that's where you get a more representative or calculation of how fast you can read and write from memory. And that's why this stops moving and it saturates at this point, okay? The explanation for this ramp up here is a bit less simple to explain. Around here, you have smaller arrays. There's more overheads going on with like maybe the loop, like it, maybe calling the function has some overhead, or the OpenMP has some overhead. It's not that easy to explain why you see this ramp up here, but in any case, this bump up here and this saturation down there can be explained by this phenomenon of dropping out of cache as you make the array larger. So now this performance here is, I will argue, more representative of what you would get if you had this kernel like this in a scientific application, because usually you don't have the same arrays and you're just reading them over and over again from cache, right? Usually you're changing their values, and then you want to do an operation on them, or and then changing the values again, and then so the reading from memory is most likely so doing the computation while reading, the data from memory is probably more representative of a typical application that you will have on to run. Okay, so the next part of this exercise, which I will name task B, is to modify this SOA, the file that ends with SOA. So first of all, you should copy the floating point, the number of floating point operations and the number of bytes of IO that we filled in the previous example into this file, soa.c. But then you have more to do. So here, basically what you have is the same. It's exactly the same. Well, it's more or less the same operation. Just the structure now looks like this, and this VL is defined to be 4 in the program. Doesn't have to be 4, but here it's defined to be 4. And so now what we want to do is basically go from arrays of this kind of type, right, where you had an array of this structure where you have X, Y, Z, T, etc. You want to sort of fold partly this index here, I, into two indices, I0 and I1, right? Where this I1 runs from 0 to 3, 4 elements, and then this I0 is a quarter of L, of what it was. I'm writing N here, but I really mean L, sorry. Okay, so what you need to do in this kernel, apart from copying the to do A, so beta FP and beta IO calculation, and apart from copying that into this code so that it reports the right number of floating point operations, what you need to do is come here into comp S and complete this because it's missing. So the calculation is missing. So you have to appropriately loop over the array. So now we're doing the same number of floating point operations and the same number of bytes of IO, right? So that's why the calculation of beta FP and beta IO were exactly the same as before. So if we have to operate on L elements, this shouldn't require and doesn't require any more bytes of IO or any more floating point operations. And so I'll give you, it shouldn't take too long, so I'll give you about 10 minutes to do this. And then similarly to before, if you make B, this will compile it, and then run b.sh, and then this will run it, and then you get a plot comparing that performance with the previous one. Okay, so at 5:05, we'll do the solution together. Or if you want to ask any questions, you can also do it now about the previous one. So in case it wasn't clear, what we want to measure is the time per single call of this comp S. And what I said was that T0 ACK is actually the average time per call, which is why in our solution, I'm putting it in here again, we only divide it by T0 ACK. Maybe ACK is not a good name for this variable because it's not accumulated, it's the average. I mean, this I can argue about. I can agree, with, but I do claim that it is the average time. T0ACK is the average time it took to run CompS once, not nrep number of times and not n small number of times. Okay, so I'm just going to go ahead and copy this, put it in. So copy the calculation of FP and IO, put it in SOA. Go. Oh, it's already there. It's already there for you guys. Okay.
No.
Oh, when did I do this? Ah, I'm looking at something else. Okay. Okay. But that's okay. Okay, so here. Okay. Okay, here is what you needed to complete. So this was empty from there. And this is not a unique way to do it. But for example, you can have two iterators like I and J, and just just traverse it this way. You can do it with temporary variables the way I did before, but okay. But I think you got the idea, right? So the array index, the index of the ARR variable has to go from 0 to L over the L, whereas the index of the individual members X, Y, Z, and T needs to go from 0 to VL minus 1. Okay, and if you compile that and run it, then I just find my browser. Right, then you'll get something like this. Okay, it's not very impressive, admittedly. So it improves a bit up here. In the case of my laptop, not so much where it saturates, and on the cluster, on this 8-core cluster, it just improves slightly down here where it saturates. And that's not all too surprising because basically I just arbitrarily went here and defined this vector length, VL vector length, to be 4, but in general, this vector length is architecture dependent, right? It depends on the architecture. So how wide these vector registers are depends on the type of CPU that you're running on. So very old CPU this would be 4, but modern CPUs have much wider kind of vector lengths. And so I'm not making as much use of those registers as I could. And so in task C, you don't need to change any code. You don't need to do anything there. Basically, if you have already set up your code, so if you've written this task 2, you completed this task 2 kernel appropriately, then what this task C does, this run c.sh script, what it does is it does this loop over L, it wraps it around another loop where it recompiles the code each time for a different vector length. So it goes from 2, 4, 8, 16, 32, 64, 128 to 256. And so now instead of having just one of these files where you scan for L, you have one for each vector length. And so if you do this, if you run it, and then you plot it, and then you plot it, then you will get something like this, which looks a bit messy. But basically every color is a different vector length. So we have the results from before, which are the circles here, these red circles, and you can make it out there. On this side and on that side. And then as we change the vector length, the shape remains about the same, but it might peak somewhere else and might saturate somewhere else. And maybe a better way to look at this is if I do it on a log scale. So that's the next slide. It's just these data, but on a log scale. And what you can see is that in both cases, both on my laptop and both on the cluster, and hopefully also on your system, you will see that for some value of the vector length, performance there has reached the peak. And actually what you see is that as you increase it, you're basically stuck for a few values down there at around 10, well, in my case, it's around 10 gigabytes per second. But then as you increase it and you reach the optimal one, it sort of jumps, maybe with one or two intermediate values to having that. So this is not, okay, now it's on a log scale so that we can look at it a bit more clearly, but I have to say this is not a trivial sort of jump, right? So basically you can do this operation in almost twice the time just by doing this very simple data layout transformation. So you can basically double your performance just by having some considerations about, in this case it doubled, okay, on my laptop. Here it's a bit smaller, but just by preparing your data layouts in a specific way. So it's almost 15 past, so we'll cover this again in the next lecture. But do try to do this also at home. Well, I guess most of you already are at home. I mean, between now and the next lecture. And of course, we can cover this again at the beginning of the next lecture, and then move on to the next exercise. Pedro?
Yes.
Can we begin 15 minutes earlier next time?
Okay. Okay.
Rather than adding 15 minutes, we add 15 minutes to the duration, but we start earlier rather than finishing later. Is that possible?
Next time is on next Thursday. At 3?
Next Thursday.
So
I think it's the same time, right?
Okay. Fine.
Can you upload your solution to part B? I'm not very good at C, and I'm getting segmentation faults with my answer. So,
is it okay if I put this in the chat?
yeah, sure. I can copy paste. Thanks.